Let's incorporate to this problem now some logistic and practical considerations. Under the conditions of the area, it would be difficult to collect 56 samples per village. A more feasible target, given the need to ensure quality of processing and data collection, would actually be 30 sera per village. Obviously, reducing this sample size at village level will reduce the probability of detecting an infected animal if present. So, what would be that probability of detection then? So, to reach 95% confidence, 56 animals were required. Now we want to collect fewer samples, we'll reduce the level of confidence. So, if we are going to reduce the level of confidence, let's try with 90% and see. So, in this case, we need 44 samples, but we want to take 30. Then we further reduce the confidence level. So if that happens, if we further reduce it to 80% and we need 31 samples, we have to reduce it a little bit more. Now to be 79% confident, 30 samples are required. This is the sample size we were looking for. But before we were at 95%, but before we were 95% confident at the village level, and we had to collect 56 samples from 308 villages. Now we are less confident at the village level and 79%. This will be compensated by selecting more villages. How many villages would have to be selected to achieve the standard probability of detection of 95% if only 30 sera were collected from each village? That's now the next question. This is the formula to calculate the required number of clusters, as you can see. But previously, with 95% confidence at village level, the result was 308. And where is the difference now? In the number of clusters that can be detected, the affected villages continue to be 80. Well, that means 1% of 8,000. But now the probability of detection is 79%. That deficiency is compensated by increasing the number of villages to include by increasing the number of villages to include in the sampling, which is now 369. The total number of required samples now is 11,070. Before it was more than 17,000. This is a further gain in efficiency without compromising the overall probability of detection. Moreover, the design of the sampling now accommodates the practical constraints of the field situation. All the calculations we have done so far considered that the diagnostic test was perfect. It had 100% sensitivity, that's what we're thinking. But now this is actually never true. The sensitivity is 95%, meaning that out of 100 infected animals, we are going to detect 95 only accurately. This lack of sensitivity will be compensated by increasing the sample size. And let's see. We had decided that 79% was an adequate level of confidence because we wanted to sample 30 animals per village. But now we have an imperfect test with a 95% sensitivity. To compensate this, we need to take more samples actually. And we don't want that. So we still want to take 30 samples. So what do? So we have to further decrease the level of confidence. Say being 77% confident reduces the sample size to 30. So how many villages are required in this case now? Again, we are less confident in the first stage. we compensated that by selecting more villages. In this case, 379 are required. Therefore, the final sample size will be 11,370. So 300 samples were added to compensate the lack of test sensitivity. So by judicious balancing of sampling between and within villages, you can see that it's possible to obtain a significant reduction on sample size while we still maintain the same overall probability of detection.